In this video, we will compare and contrast continuous versus discrete optimization. Oftentimes, our choice of an optimization algorithm begins with this distinction because it has the most to do with the nature of the problem and the dataset that governs the course to follow for optimization. Take any dataset you can see in your head. For most human beings, we are only capable of coming up with a very distinct, finite dataset. And for most people, these datasets will consist of very common numbers, like integers or other familiar numbers. A dataset like the one you just thought about is called a discrete dataset, where this dataset can be separated into very separate, or discrete components. Another example of a discrete set is the set of nodes and edges that topologically represent all shapes and geometries. In comparison, a continuous dataset is a dataset that can have infinite elements. An example of this is the set of positive integers. Another example that is far easier to envision is a continuous function, like y equals x. While you can reduce this continuous function into discrete subsets, you can keep adding and subtracting to the subsets and still not get the whole continuous picture of the dataset. Now that we have discussed the differences between continuous and discrete optimization, let us discuss how they can also work together. As we previously discussed, continuous functions can be made into discrete subsets. Though we are bound by the inconceivably large bound of infinity, the truth is, our optimization abilities are more bound by the computer's ability to process information. Therefore, continuous functions are normally represented by discrete sets. The larger these discrete sets are, the more accurate, or optimal, the optimization becomes. Next, if we have a discrete set, we do not necessarily know the dynamics between each element of the set. As demonstrated by continuous functions, we can keep adding elements to the sets and still not get a 100% complete discrete representation of the continuous set. Therefore, in order to quantify the dynamics between each element, continuous optimization is used to fill in those blanks. Finally, let us discuss where discrete and/or continuous optimization could come into play. Discrete optimization would mostly be used in integer-based optimization, where solutions can only be based on the input integers. An example of discrete optimization would be route minimizing algorithms, where the goal would be to reach all the destinations in the shortest way possible. Other areas would include supply chain management, stock market trading, and other applications, where you have a certain, finite amount of elements that you're working with. In comparison, continuous optimization would involve more calculus-driven processes, such as in product design and manufacture where you want to minimize the amount of material you use, or in the quantification of physical processes in physics, where time is considered to be the continuous variable. Thank you for watching this video. See you in the next video.